the middle column, or well, one of the middle columns here, incomplete, because when you find the z-score associated with the data point, we rank the data, right? So data has to be in ascending order, and we rank it based off of its position within the set, right? So that's the easy part, right? What we do is we take the average of the number's rank and the number that came before it, right? So in this case, 0 plus 1, right? Because the data point that would have come before 24.9, if 24.9 is in the first position, that number would have to be in the 0th position, right? So we take that, divide it by 2, and then divide the result by 9, right? Because there's 9 values in the set, right? So what we're doing is we're getting a percentile. Right, and that's actually the technique, and we'll explore this in more detail down the line, especially in probability. That's the technique that we use to find a percentile rank. Now, if I take this, multiply it by 100, and round it, I would come up with 6, and I would say that this number is in the 6th percentile. Right, and what we define a percentile is the percent of area below a particular number, right, or less than that number. Right. So what this is saying is if you had a full distribution with many, many data points, the number 24.9 would be ahead of about 6% of them. All right. Now, this is a very small sample, so it's not overly meaningful, but that's essentially what the distribution is going to indicate for us. All right. So what we would do is we do that for each of the remaining values. So this is the second position. So the 28.5, so I would do 1 plus 2 divided by 2, aka the average of 1 and 2, 1.5, and divide that result by 9, and get the percentile in decimal form. All right. In terms of understanding the process, not too crazy, but in terms of actually carrying it out, fairly tedious. What we could do is use a table approach, because this value here essentially ended up being, more than essentially, it is 1/2. This one is 1.5. The next one, logically, if we're following the sequence, would be 2.5, 3.5, 4.5, and so on. All right, so 2.5 divided by 9, 3.5 divided by 9, and so on. All right, but let me show you how you pop that into the calculator. All right, so we go to statistics. So hit the home icon, go to statistics, go to data, because we're putting data in. I can't bring myself to do it. I just can't delete this data knowing that I'm going to have to use it again. So I'm going to go into a V3 here. All right, I could fill it with a formula. What this will do is it'll give you a sequence of values starting wherever you want it to start. All right, so if I go, well, I could use this one, or I could go into the toolbox. If I use empty, let me hit enter on empty. Go into the toolbox. You have a lot more options. If you go into the list menu. All right, so you can create a new list of values. This one is really exactly what we just were looking at, except it says f of k. It lists values for f of k for any number 1 through n. All right, so basically what I'd be doing is writing an equation, but this one gives me the flexibility to not just go out to the 10th value. I can go out to whatever value I want. All right, so I can put in an expression here. If I put in 0.5, for example, that's just going to populate the list with all 0.5, so that's not very helpful. All right, but if I put in a 0.5 plus k, where's my k? Oh, you know what? Little nifty trick. I didn't even realize this until I accidentally stumbled upon it. That XNT button brings up a k if you're using this function. All right, so that would be, oh boy, you know what? got this thing for a reason. Doesn't show up on there though, right? Anyway, that button, the X, N, T button, right? It's a whole lot more than just X, N, and T, right? Depending on what function you're in, it'll bring up different values. Now, if I start this at 1, that's going to make my very first entry 1.5, which is not what I want, right? So, oh, sorry, if I end it at 9, it's going to start at 1, and that's going to be a problem. So what we can do here is just subtract a 1 from this, all right? Which is really the same as saying negative 0.5 plus k, right? Because negative 0.5, even though it's not an entry in the list, if I add 1 to it, it's going to give me a 0.5 and then a 1.5 and then a 2.5. So then I just need to know where to stop. But if you overshoot it, that's not a big deal. And honestly, you probably could have typed in all these numbers already and been done with it. But yeah, I'm just showing the technique. So if I say, for example, go out to 9, all right? So the 9th value would be 5.5. You just ask yourself, is that what I want? All right. So the 9th value. Oh, actually, no, I'm sorry. It would be 3.5. Yeah, 3.5. So I want it to go one more value. So I'll go to the 10th and then hit OK. And it'll populate all those numbers in for us, which is great. All right. And if I overshot it, that would be an issue. I did overshoot it. All right. So I'll just delete the one that I don't want by hitting clear. 8.5 should have been my last entry. All right. Now, so that means I should have gone out to 9. What I can do, instead of doing it a piece at a time, because we only have the 3 lists to work with, I can do basically the same thing. All right. So the unfortunate, we know this, and you can sort by increasing values, but I want you to start thinking about how you can write simple linear equations to populate lists, because that's going to be more useful. All right. So just going back to empty. So basically the same thing, but this time I'm also going to have it divide by 9. All right, because I wanted to do it all in one shot. So 1/9, oops, parentheses, 1/9. Okay, that's not working. We'll do it after. Times 1/9. 17th time is the charm. All right, so we'll do the shortcut here. Negative 0.5 plus my k, and I'll go out 9 values. All right, and so that'll populate the entire list for us. All right, which is great. So all of these decimals, so 0.167, 0.278, and so on. 0.389, 0.5 even, 0.611, 0.722, cut out a lot of the work, 0.833, and the last one is 0.944. All right, so we got this by doing negative 0.5 plus k on the interval of 1 to 9, so k is less than or equal to 9. And then for this one, we took that expression and divided it by 9. Right, so same as the previous one, just divide by 9. But what I want to do is get all the z-scores for each of these entries. All right, so that's a little bit more interesting, right? Because there's another function that'll determine z-scores for us, all right, given a particular percentage. It's more of a unit 2 concept, but it's kind of necessary right now that we talk about it. It's the inverse norm function. All right, so it asks for the percent, the mean, and the standard deviation. also in your toolbox. All right, so I'm just going to go out to the home screen here real quick. I have it up from before, but if you go to your toolbox, you got to backtrack a little bit, but you're going to go to probability. So let me just zoom in real quick here. So toolbox, probability, then you're going to go to distributions. Kind of feel that it's necessary to write the word now. Distributions, and you'll see normal. We're kind of living in the normal distribution world right now. And then if you go down, you'll see inv norm, A for area. Area and probability, as you'll discover down the line, are synonymous, all right, when it comes to normal distribution. So toolbox, probability, distributions, normal, all right? And that'll get you to the inverse norm function. So what I can do is, I already did the first one. That's how I actually got that negative 1.59, just using this function. I just did it on a TI, which essentially works the same way. But let's say I want to do it for the second one. I could put in a 0.167. Right? The mean and standard deviation should be 0 and 1. All right? Because this is a standard normal distribution. Whenever you standardize, you're taking data points and really just kind of transforming them to be on the scale where the mean and standard deviation are both 0 and 1, or are 0 and 1 respectively. All right? So that's the justification for that. And we would get negative 0.966. All right? But again, it's computation down a list. It's really frustrating, especially if you have some experience with Excel, because you know that you can operate on entire columns of data all in one shot. All right, so that's kind of how we want to approach things. Whenever you have a list of data and you have to run a computation, you really don't want to be doing it manually. You want to come up with a rule that applies to an entire list. That's why I overcomplicated the process of putting in the sequence values, because it may not be such a short list. There could be like 300 values that you have to put in. And if you have a rule that allows you to put those 300 values in, like in Excel, it's the sequence function. You just tell it what the difference between the values ought to be, and it'll populate a list for you. You just tell it what the length of the list should be. All right. This is not quite as simple as that, but it is an avenue that we can approach. So back to the statistics. I have all these values here, but I want to be able to take those values and apply my inverse norm function to it. So now I am gonna I'm gonna steal my list 2 here. I think I'm done with it anyway, but I'm gonna fill with a formula. Empty. I mean, you could look down the list to see if what you need is there, but we talked about it last time. It hardly ever is. So, and they're working on the new update, so we'll see. But I'm going to hit empty. I'm going to select that inverse norm function. So go back into the toolbox, but instead of putting A, like whatever that individual probability or area was, or percentile, I'm going to put the values in V3. So shift alpha division, shift alpha division, shift alpha division. Fat fingers aren't working right today. Actually, I can't even tell. Yeah, that's definitely lowercase still. And this app doesn't have a confirmation, like a blinking cursor on it that I can tell that I actually hit a button. So shift, then alpha, then division to bring up the V. All right, that was V3, standard deviation 0. I'm sorry, mean 0, standard deviation 1. And then you hit OK or execute, and it pops in that list for you. All right. The reason it's grayed out, even though we don't really need it just yet, is because I have more values in the frequency column than I do in the V2 column. So I just delete those, however many there are. There's a lot. I suppose there's probably 30 of them. You know what? It doesn't matter if it's grayed out. But we have the values there. thing's jumping around on me. So these would all go in the list. So negative 0.589, negative 0.282, 0. Then we have symmetry, which doesn't always happen, as you know, because we just went through a whole lesson on skew. So the fact that this is already showing to be symmetric is interesting information. Oh, I don't know why I hit zoom. I'm just like a mess trying to like actually accomplish anything. Paste is what I wanted to do. And then I just have to plot these. Negative 1.59. All right. So I'm plotting my first column against my last column. So I'm going to plot those against one another, and that's going to give me, well, obviously a graph, but it's going to give me a sense of whether the distribution is considered normal. All right. I can tell you that in these normal, they're called the normal probability plot. In a normal probability plot, if the arrangement of the data points is close to linear, then your original data set is close to being a normal distribution.
So the z-score is the x variable?
The z-score will be the y variable.
Okay.
So 24.9, and we're just going to ballpark this, but 24.9, negative 1.59. So a little bit short of 25, a little bit below negative 1.5. That'd be 1 point. 28.5 and negative 0.966. So that's going to be like here. Then we have 29.4. So that's going to be just a smidge further. It's going to be like here. All right, so because it's going by twos, the 29 would be halfway between the this tick mark here and the 30. So I guess maybe I could shunt this over a little bit, but negative 0.282 goes along with 32 and change. So it's a little bit below, like about right there. 33 gives a 0. Oh, did I say it's going by twos? It's not going by twos, it's going by ones. But I kind of plotted it right, but that last one I gotta fix. 1, 2, 3 is where it should be. There we go. And the one prior to that, 32.1, should be a little bit over. Honestly, I think I tricked myself. And then everything else is going to be symmetric the other, on the other side of the axis. So 33.4 and 0.282, like here. 36.2, a little bit more than 0.5. 38.1, a little bit shy of 1, and then 40, a little bit over 40. Oh, I put a negative here. I meant to put a positive. I did a straight copy job of the first one. 1.5-ish. Yeah, so something like right there. Now, aside from, like what's going on over here, which may or may not be as accurate as I would like it to be, we are looking at something that does seem to be moving in a kind of linear direction, right? It's always a question of, can I slap a ruler on it and have not too much deviation between the points and the ruler, or in this case, the line that I just drew, right? So this looks like it's hovering around a linear equation. Whatever that linear equation is, we don't actually have to find it. But, I mean, we could do a regression to see what the R value is, if it's close to 1 or close to -1, in this case 1 because it's going uphill. We're basically, we're taking z-scores and treating it like another variable. So we would actually be applying a bivariate technique to a univariate data set, right? But it would get the job done. But you really just need to eyeball it, right? So the distribution of the normal probability plot is close to linear. Therefore, the distribution of the data I'll say data set is close to normal. All right. Unfortunately, this is one of those explanations that you have to be fairly detailed about, because if I say the distribution is close to linear, making the distribution close to normal, so any reader is going to look at that and say, well, which one is it? Is it linear or is it normal? Right? So we need to really emphasize that the distribution that we're talking about being linear is that of the normal probability plot. And then that follows that the original data set has to be close to normal, right? I would say it outside of an academic environment, basically a textbook, I would not expect any of the points to be really this close to linear. Okay, so if you're talking about real data, you know, so we would say approximately normal or close to normal, or you could say it looks like it's probably normal, so I'm going to use normal probability techniques. But if you look at it and say, I don't think that's really normal, then you can disregard all my calculations. I mean, that's really how statistics works. You know, so when you collect data and analyze that data, you want to be able to analyze it using appropriate techniques. If I don't know that a data set is distributed normally, then I can't do things like you might remember in the past, like a binomial distribution. You know, normal distributions are familiar. You've seen that in one of the algebra classes. But, you know, like what happens when it's not normal? You still do those techniques, but you put a little caveat in there that, well, I probably shouldn't be using these techniques, but that's all I have. All right. There are some what we call non-parametric techniques that we'll get to later in the year that allow you to focus on instances that are not normal. But we could also normalize a data set by applying the central limit theorem, right, where appropriate. Right. Bless you. So that's the one where we take samples from the sample or samples from the population multiple times and find the average of the averages and find the standard deviation of the averages. It allows you to take any distribution, whether it's highly skewed or heavy-tailed, and apply normal distribution techniques to it. None of which we've really covered yet, but this is all part of understanding what makes a distribution normal. All right, so how does this help? If I know, it's like reverse engineering a solution here. So it's applying the logic. If I know that a distribution is close to normal, then I know its skewness is that, well, if we're addressing skewness, we're saying it's symmetric. All right. If I'm addressing kurtosis, I'm saying that it's mesokurtic. All right. So I can draw my conclusions about skewness and kurtosis based off of the normal probability plot, right, which is a good thing to know. All right. Now, you might have noticed that at no point when we were doing our computations did we actually use the data points. All right. We only used their rank. So we're comparing rank with that of a z-score. All right. So then it begs the question of, well, what if you have multiple values that are the same? You know, let's say it's multimodal. All right. You would still have to rank the values, except let's say you had 7 24.9s. Though all 7 of those 24.9s would have to be accounted for. So you would rank including the repeated values, right? Now, as far as the calculator is concerned, and when I mean the calculator, I'm talking about the built-in functions. Let me clear this table V2, N2. I'm going to put the raw data in, and you'll see, spoiler, there's a normal probability plot option, All right, so just get this data in here. I think I got them all in right. We will find out right now. So go to graph. See the option that says normal probability plot. That's heartbreaking. All right, this is a big old mess because I have multiple data sets in. All right, so if you don't want it, sometimes you can have multiple data sets plotted. Like if you do a box plot, they'll be separated from one another and you'll see which one is which. It'll be pretty easy. But sometimes it looks like this is a hot mess. So let's go to data, value v1, clear it all. No, turn off the function where it says show in graphs, graph and stats. All right. So then you could just focus on the one that you're interested in. All right. It'll gray it out, so that means it's not active. And now I have the graph that I'm interested in. And you could truncate the domain if you want. I turned off the first one because that was the one that was really in the way. But you see those green points that are plotted there. That's my V3. So, but you could see here that it looks pretty close to normal. If you need to fill out a table, which I'm going to have you do when we take a test, you can get the points when it says expected z-score. You can get the points directly from the graph. All right, so those y values. All right, so that's pretty useful. If we go back to the original data set, we can now apply the normal probability technique. Let me just wipe this stuff out now. All right, and I'm going to turn this one back on. Show in graphs and stats, graph and stats. So I'm going to take a look at the normal probability plot for this. And you can see, I mean, just based off of this graph right here, that you can't make a claim that this is going to be a normal distribution, all right? Because it's the points are not following a straight line. In fact, it's not even close, all right? So we're looking at something that is not a normal distribution. All right. And again, because the distribution of the data in the normal probability plot is not close to linear. All right, that's what we call the worst case scenario. Because it's not close to linear in the normal probability plot, which means it's not a normal distribution, which means I can make no determination as to the skewness or the kurtosis. All right, we want it to be a normal distribution, ideally, because if that's the case, then we could draw the conclusion about the skewness and kurtosis. So for questions 1, 4, and 7, we had, just going back, so for 1, we had 0.0948 with no significant skew. So you got to write it small here, but 0.0948, and I'll say no skew, just simplify it. All right, the kurtosis value is negative. All right, if I remember correctly. Yeah, it was negative, so it was platykurtic. And then we would say that this is not normal. All right, so in terms of a conclusion, what we got from this is that the graph, it doesn't have any skew, so it's not leaning one way or the other. It's getting close to the x-axis fairly quickly, so it's light-tailed. All right, that's our platykurtic case. But remember, in the instance of platykurtic, you could have really anything going on in the middle as long as it feathers out towards the x-axis fairly quickly. All right, so what this is telling us is that we really can't draw a conclusion about the nature of the graph. So not, I'll say, feasible. I think I spelled that right. All right. The conclusion is that it's not feasible to come up with a conclusion, really. I mean, I can't tell you what the graph looks like, because we could be looking at something that looks on the ends nice and platykurtic, no skew. So I could be looking at something like this. I mean, it could, I mean, there was a little bit of skewness. So depending on how you visualize it, I mean, it could be anything, you know, like it's going to be roughly symmetric, but not perfectly symmetric, right? If the skewness value is 0, it'd be perfectly symmetric. So it'd be a little out of whack, but you know, something along these lines. Maybe slightly longer in the tail on the right-hand side, but you know, like that's one possibility. I mean, it could also be like that, right? So it's not a normal distribution, but it is platykurtic and has no skew, no appreciable skew, right? So a lot of stuff going on in the middle here that we're not able to make a decision about, all right? So I did the worst case scenario for you. The other two instances are gonna give you some more meaningful results, okay? So I saved that for you. All right, so what I'd like you to do for today is at least questions 2, 5, and 8. All right, if you get through that, then, well, tomorrow we're going to continue with this with the goal of finishing it by the end of class tomorrow. So, so if you want to do this on your own, you know, at home or whatever, just tackle it. But yeah, that's what we should be looking at this point. All right. And that gets us right to the end. Look at that. Kurtosis. Gotta love it. Say it again? Okay, so it's not a short explanation, but I can tell you that the first thing that you need to do is find the mean identification. You're welcome. Take it easy. Yeah. So then the second thing you're going to do is figure out what, so the mean is x bar, and s is the standard deviation. So you're going to figure out x bar minus 2s, and then x bar plus 2s. Thank you. You're welcome. So then after that, you're going to figure out what the percent of values from this set is that falls between those two numbers.
Okay.
I'm not gonna be here tomorrow. Are we just working on the packet?
Yes, and just try to bang out the rest of the packet.
Alright.
I'll get videos of. So,
Thank you.
and then there's more to it than that, but
There is?
yeah, because then you have to do. Oh, I'm sorry, that should have been a 1s. Those are both 1s.
Oh.
That was my fault. The next one is going to be x bar minus 2s, x bar plus 2s, and then x bar minus 3s, x bar plus 3s. So you're just changing the 1s to 2s and 3s.
I was just wondering what day you usually have actually go.
Today after. Perfect.
Alright, today's actually not gonna work for me, unfortunately.
Okay.
But I'm happy to come next week.
All right, sounds good. I also have some frees if you want to come by during the day.
Perfect.
2, 4, no, this is 4, 2, 6, 8, 9.
I thought you just have 6, 8, 9. I saw that. I didn't know you had 2.
Oh, I do have 2. It's just I think when you asked, it was after 2 already happened, so it wasn't on my radar.
Gotcha. I'll try to work through some of those packets, and if I have any questions, I'll let you know.
Sounds good. Thank you. Right. All right. Oh, you know what? I gotta stop.